Hi everyone. In this video, I'm going to go through how to implement a diffusion neural network to denoise images. Then I'm going to go through how you can take this neural network that you've trained to denoise images and deploy it on complete static to create completely new images. The example I'm going to go through is with a fairly simple dataset called the fashion MNIST dataset. Uh, but the code used can easily be expanded to much more complicated data sets. So before I go into the code, I just want to give a really simple overview about how this method worked and how I implemented it. So the first thing we do is we take our images, see this one's a t-shirt or a sandal, and we add static noise to it. We add noise from a Gaussian distribution to cover up the image. Then what we do is we take our noisy images and we train a diffusion neural network to be able to pick up where the underlying image is and where the static noise is. Then, once we think we've trained this neural network sufficiently, what we can do is we can take complete static noise, um, and what it'll do is, because it's so overfit to the images that we fed into it, is that if we keep feeding this static or the outputs of it into our neural network and then keep adding noise and then keep feeding it through the neural network, eventually it'll hallucinate a distinct image under the static. And this is how we basically generate new images similar to the ones that the neural network has been trained on. So jumping into the code here, the two things worth note is one, this project was done in completion of my master's in statistics, and it is largely based on a paper called Denoising Diffusion Probabilistic Models. And so if you want more information about the more theoretical side of how this method works, I'd recommend reading that paper. And also, a big decision choice was using PyTorch um, instead of using TensorFlow, which is the other popular library for implementing neural networks. And obviously, with some of this code, it's really just about setting up our GPU because neural networks are very computationally intensive to train, and so we use the GPU. This is just kind of loading in our package, kind of simple stuff. And then we get here, and this is basically explaining the specific way in which we add noise to our image. So we do it on a beta schedule, which follows the equation here, where b tends to be quite a small value, or the step for all values of t. For example, here just the default is between 0.02 and 0.0001. So quite small values, which makes our alphas here quite big. And the product tends to decrease smaller. And this is basically the ratio at which we add noise to our image. So if you see here, we have our square root of alpha, and then the 1 minus the square root of alpha. And then what we do is we take our image x0, and then we add noise based on the beta schedule. And this is basically what it looks like for different time steps. And then if we decide to add or make our beta values larger, like starting at 0 0.01, 0 0.2, I've made a plot to compare it to whether when you make your beta schedules significantly smaller or beta values. And this is basically what it looks like. As you can see, when you make your values for beta quite large, it tends to blur the image a lot faster. And when you make them smaller, it tends to blur the image a lot slower. So this is just information about how we actually added the beta schedules. For all intents and purposes, our default values of 0 0.01 to 0.02 were used. And then the timestamps were picked at complete random values for small t here. Then a second thing, which is kind of unintuitive that we need to set up, is our sinusoidal position embedding. So when we add noise to the image, we basically do it on a time step. Like you can see in these images, some of them are a lot more blurry than others, and we add different time steps to them. Like some of them might not have a lot of noise, some of them might. And what we do here, which is really helpful to get the model to pick up on different time steps and kind of understand different noise values, is we add sinusoidal position embedding. And this basically, when we feed the image into the neural network, we basically add values based on this equation here to the image. And then the model basically learns these position embeddings and it helps them understand the time and helps them get better, more accurate denoising models. And so I made a few plots of what it looks like for different dimensions and time. I'm not going to go through too much detail about how it works. It looks nice. And you basically add this to our image at different points in the training process of the neural network. Then finally, we get to our actual architecture of our neural network. So if you ever seen an image of a neural network, basically our neural network follows a similar rule where it expands its layers and its nodes, and then it kind of smushes them down back to its original size. And so what this block does, what I've called the class block, pretty uninspired name, I must say so myself, is that it takes input channels and then it takes the output channels and then it has a Boolean flag for whether we're going up, we're increasing our channels, or we're going down. And if we're going up, then our input channel doubles, but our output channel stays the same. And if the and if we're going down, then we decrease the size, our input channel is smaller, our output channel is smaller as well. And then these are just some kind of standard transformations we tend to do. And the other part is that we have a linear component, and this is the sinusoidal position embedding above that we actually later in the forward diffusion process, we actually add a value of t to our x, which is our kind of morphed image that we'll later see. And this is basically how we add the position embedding to our neural network and quite a few other convolutions. Then this is the main class. This is the main neural network architecture that we use. And these are our up channels and our down channels. So we have a time dimension, our position embedding, and then we have a linear transformation of that. And then we have just a simple value transformation. Then for our convolutions, we have these up channels. If you notice, they basically increase and decrease. So a down channel goes from 64 to 256, and an up channel takes it from 256 all the way down to 64. And this is basically seen here, and this is where we utilize our block class, which increases the channels and decreases them. So here we have the down channel as our input, and then it expands it upwards to, it doubles it to, for example, on the first downward convolution, it brings it up from 64 to 128. And this is, imagine it, we're kind of expanding the image and its values times different neural network parameters. And then for the downsample, we have expanded it. Oh my God, it's 256, size 256. And we decrease it down, we smush it down to 64 again. And then we do a simple final 2D convolution. And then finally, in this forward process, this is where the main training happens, or this is what the training process uses to optimize. And so we take our time step, we use our position embedding that we see up here. We put a linear transformation and then a value. Then for our x value, we add an initial convolution, and then we loop over our downsample convolutions to expand the image and the information we can get out of it. Then we next use our upward convolution. And then also, what's kind of cool is that we append the information from the down tracker, or we append different information that we previously had for the downwards convolutions. And then we do a final convolution, and then we return x. So this is basically the neural network architecture. And this is where in PyTorch, we're trying to optimize the hyperparameters, or not the parameters in our neural network. So finally, after we've got all that, we need to define our loss function. So our loss function is basically we have a noisy image, we know the noise, and then our model tries to guess correctly where the noise is. So this is how the loss function works, is that we use the diffusion equation all the way up above. And then we use that to get the noise, and we get our noisy image. Then we use our model. We take our noisy image and the time step to get our noise prediction. And then we simply just use a mean squared error loss to get the loss between our noise and our noise prediction. Then this is a bit of code that I've done, kind of making the loss function a bit extra, which returns the loss function at different time steps. So when the time step is below 100, when the time step is between 100 and 200, and when the timestamp is greater than 200. And I'll use this information later on to kind of understand better how the model learns at different time steps. And then this is a flag for whether we return our noisy image, just to get some more imagery about how the model learns over time. So now we get here to the training loop. Um, so this is pretty self-explanatory. What we do finally, we've created our wonderful model. We've created the target of our noisy images and the of our images, and we've created our noisy images that we use the model to train on. And finally, we set up a training loop with, of course, the basic stuff. We have a model, we have the learning rate, the epochs, and we want to show the loss. This is kind of just outputs for tracking when you're training. We use the Atom optimizer, which I recommend looking up if you want to learn more about how the model trains, or hyperparameter optimization. And then for our epochs, we train the model, we put it in training mode, we keep track of our losses and number of iterations. So we have a step and our batch. And then we get our image, of course. We get our timestamp, which is a random integer between 0 and t, where t is 300. And then for this is just a flag that we want to collect some of the images. And then otherwise, we want to get the loss, which is where we take our model, we take our x0, we take our time step, and of course the model predicts, and we create our noisy image, that we create our prediction from the model, and then we guess how far off our model was, or the loss between our model's predictions and the actual image. And once we've gotten the loss, we can optimize our model using these two steps, and then we can track the loss, obviously, for just information to be used after the model is trained. Then we show our epochs, and then we just keep track of it. So really the most important parts are getting the loss here, what's going on in the loss function, and then optimizing here. And the rest of it, it looks complicated, but it's really just keeping track of the results over time. And then finally, get our model one, which is our simple UNet, define our number of, print our number of parameters, which is nearly 4 million. We have a learning rate that I kind of found to work best over just trying different ones, and then number of epochs is 50. Okay, so after we've got our model, once we've trained it, beautiful, we've gotten tiny mean squared error. We're going to do the final part, or the second stage, which is we're going to take our trained model and use it to generate new images. This is the code to do it. So this is basically each iteration. We take our betas, we calculate a square root of our alpha or cumulative product alpha, and we can basically calculate the predicted image and via the equation here. And then basically this code here adds more static noise based on the posterior variance, which we calculate kind of the same as what we have up here. I won't go kind of too deep into the maths. And then basically we iterate, we keep returning in this code our sample. We use this sample time step and we iterate over it 300 times till finally at the end we have our best image, or we have actually all the images. And then we get the last one, which is our predicted image. And then going all the way down here, this would be a sample of what they would look like. Obviously, you can see I probably haven't trained the model sufficiently. And so you get some of them which kind of look like nonsense. And then some of them, I've taken the best ones here, look like distinct images that are based off the images that you see in the MNIST dataset. Then here I'm going to kind of skip through this. This is basically me trying to minimize the number of parameters down to 700,000 instead of roughly 4 million, and seeing what the images look like there. Then I've done some interpretation here. So this is the mean squared error at different time steps. And as we can obviously see, that for different time steps, the losses tend to be notably different. And some of them like even flatline at certain time steps. And then this is basically comparing a weaker model that I've done to the more efficient one that you saw implemented, or not the more efficient, the larger one that you saw implemented. And this is the percentage change on the more efficient model. As you can see, kind of unintuitively, between 100 and 200, it kind of performed the worst. At less than 200, it kind of performed the best. And then these are a few examples of what the image looks like. So this is a time step 108. And this is kind of showing you how the model improves over different epochs or training rounds. So this is at the 5th epoch. This is at the 10th. This is at a very large time scale. You'll notice a large time step. This is at 15, and then finally it's going to go all the way up to 50, where we get some really clear, crisp images like this one at the end, which is, I imagine for a human, quite hard to see the underlying image. And these are a few more examples of the predictions against the underlying image. And then finally here we have the regression of the model taking the pure static and turning it into actual recognizable images. And as you can see, it kind of slowly appears. The underlying shape you can almost kind of see near the start, like here. And these are a few more examples. And that's it. That's kind of a very, very, very quick and brief overview of how I implemented this diffusion neural network. and the results that came of it. And thank you for watching.